can you kind of talk through the different ways that you approach making video models run more performantly?
Yeah, sure. In general, I think there has been a lot of work on video compression done, and where they also want to sort of factor out the redundancy in the data by a lot of ways. For example, by computing the residuals, learning the motion and compensating the motion, quantizing the residual, entropy coding. So many ways, which has been very well explored over the decades, how you can compress the amount of data to represent the video, basically, to reconstruct it well from the less amount of bit width, which is actually great. A lot of techniques are there. But these techniques are usually comes with an extra processing cost. So you have to spend more and more compute to do this compression. And so many of those techniques doesn't really speed up the performance. So our main focus was how can we sort of reuse without introducing more computation to the model, without increasing computation, just sort of leverage this redundancy to reduce the compute. And many of the existing networks just run frame by frame. So they get one frame, they pass it to the layer, process all the, activate all the neurons of that frame, then go to the next layer, run all the neurons again, and this is how they just process, like layer by layer, and every layer they process the whole frame. And I believe this is quite wasteful, and this is not the way to go. Also, if you look at your brain, the human brain, this is not how it works. If you look at the activations in the neurons of a human brain, you observe that they activate very sparsely, actually. They don't activate all at a fixed rate, and they are very sparse, basically. And they usually, each of our neurons usually fires once there is enough of the stimulus, like there is enough of changes in their input. They accumulate the amount of changes and amount of information coming to every neuron and activate once there is a sufficient amount of activation, sufficient amount of stimulus in the neuron's input. Mm-hmm. And I think this is the reason why human brain is way more efficient in terms of power consumption. It's like you use like a 6 watt versus, or normal GPUs run like a 250 watts basically. And this is also how has been inspired a lot of effort on, for example, artificial spiking neural networks. They try to mimic the same concept. They want to sort of create some neurons which have some sort of potential, and they just gather it and fire once there is enough of that, and they don't run like asynchronously. They don't run synchronously at every layer. But that also hasn't turned out to be very successful in practice because these sparse activations and basically bookkeeping of all these activations is very memory intensive and consumes a lot of energy. And also some of these operations, which happens in the spiking neurons, like this exponential decay of the potentials, are not efficient to implement in the silicon hardware. And for example, if you have an analog system, you can model this exponential decay with the current of a capacitor. So if you have a capacitor, its current decays over time. But if you want to program it in a digital computer like what we have nowadays, it requires a lot of multiplication and a lot of memory access, which is even more expensive than normal feed-forward neural networks, which we have today. So far, this mimicking this spiking neural network hasn't been so successful in the digital computers. And so I think maybe we need to, we should, still inspire and mimic this type of behaviors, but not very precisely, like way by way, because you have to just adopt the idea based on what you have. This is also what has happened to human when it wants to fly, basically, right? We initially we wanted to look at the birds and see how they wing moves, which was not successful because the human the birds are made of bones, feathers, different things. While when you want to create a plane, an aircraft with metal, is very different. So we got. We could successfully fly once we adopted those concepts to the material which we had, basically.
Right. There's a broad argument for all neural nets. It's not, exactly how the brain works, but it's somewhat inspired by how neurons in the brain work.
Exactly. I'm mentioning this example because there has been a trend in neural network called like neuromorphic computing, where we wanted to build spiking neural networks, and they didn't turn out to be so very successful compared to existing. A lot of video actually processing has been followed in that direction. And I still believe that this is a right direction to go, but we need to adopt the concepts, basically. And this is what we try to do in our CVPR paper. And for example, based on, we try to implement the concept of residuals and triggering the neurons at every location based on that, but adopt these concepts to be more friendly to the feed-forward neural networks, basically, in skip convolution.